In this video, we'll be looking at another question involving mass sliding on an inclined plane. But in this case, we are having two mass, and the question says mass is m1 is held on a plane with inclination angle theta, and mass m2 hung over the slide. The two masses are connected by the massless string which run over a massless pulley. The coefficient of the friction, and we should assume the kinetic and the static friction are equal between m1 and the plane is mu. Mass m1 is released. Assume that m2 is sufficiently large so that the m1 gets pulled up the plane. What is the acceleration on the system, and what is the tension in the string? So we're asked two questions: the acceleration and the tension. Okay, let's analyze this. Since we're told that m2 is greater than m1, so the direction of the motion of the masses would be in this way, and we as well have that there is a tension on this which should be T1, and another tension on this which should be T2, and we were told that it's a massless pulley, and in that case is T2. T1 is equal to T2, which is equal to T. And let's analyze the weight of this mass will be pointing downward. We have this, and this will be m1 g cos theta. Here will be theta, and the normal, for the fact is not sliding, there will be a force keeping it which is equal to the normal. So since it's sliding and there is a frictional force exists between the block and the inclined plane, the frictional force as well will be pointing towards this direction, opposing the motion, which is F is equal to mu kn, where n is the normal. And we have the mass and another force trying to pull this downward, which will be m1 g sine theta. So in this case, let's try to, okay, there is still another force along this because the direction is pointing downward. We have this to be m2g. So in this case, we have to solve. Analyzing this y direction, that's the vertical axis, we have that n, let me change the color this time. We have that the n, the normal, is equal to m1 g cos theta. This, let's term this equation 1. And for mass m1, the net force will be equal to the tension T is pointing upward, and both the force and the frictional force, they are pointing downward, which will be having this to be m1 g sine theta minus the frictional force, which is mu kn, is equal to m1a, which is the net force, and we have this to be equal to T1 minus m1 g sine theta minus, we have the n to be m1 g cos theta, which will be m k m1 g cos theta is equal to m1a. So this is for mass 1, so let's double this equation 2 as well. For mass 2, m2, we have this to be pointing downward, and this will be equal to m2g minus t2 is equal to m2a. So if we decide to simplify this expression, we'll be having that the tension, we don't really have T1 and T2 because they are equal. At this point, we can say that the tension T will be equal to M2G minus M2A. So we can rewrite this to be T to be equal to M2 into G minus A. So this is the tension in the string, and for us to calculate the acceleration, we need to substitute. Let's turn this to equation 3 in 2. So substituting it, we have this to be m2. We are now rewriting equation 2, which is m2g minus m2a minus m1 g sine theta minus mu k m1 g cos theta is equal to m1a. So if we decide to collect like terms, there is a here and there is a on this side, we have that m2g minus, there's m1g here and m1g here, so we have m1g into sine theta plus mu k cos theta is equal to m1a plus m2a. So if we rewrite this as well, we have m2g minus m1g into sine theta plus mu k cos theta is equal to m1 plus m2 into a. If we decide to make a the subject formula, we'll be having the acceleration to be equal to m2g minus m1g into sine theta plus mu k cos theta divided by m1 plus m2. So, and this is the acceleration on the system. So thank you for watching this video. If you have any question, feel free to send us email at science@nesa@gmail.com. Thank you.